Let's look at the rank theorem. The rank theorem tells us that the row space and the column space of a matrix have the same dimension. Find the dimension of the row space of this matrix, A, for example, 0, 8, 6, 7, 5, 3, 0, 9, 10, -2, -6, 11. The reduced row echelon form of A gives you a basis for the row space of A because elementary row operations don't change the row space. So just count the number of non-zero rows in the reduced row echelon form. This is also the number of leading variables, sometimes called pivot variables. The reduced row echelon form of A is 1, 0, -9 20ths, 51 40ths, 0, 1, 3, 4, 7 eighths, 0, 0, 0, 0. A basis for the row space of A has two vectors. Here they are, this one and this one. So the dimension of the row space of A is 2. Okay, find the dimension of the column space of A. Well, this should also be 2 because we saw a moment ago that the dimension of the column space and the dimension of the row space are the same for any matrix. Let's verify that. We can't use a calculator to find the reduced column echelon form. There is no such button on the calculator. So here's what we do. We find A transpose and then find the reduced row echelon form of that, because the column space of A equals the row space of A transpose. Here's A transpose. So again, all we did was take our matrix A and transpose it. So what used to be the rows are now the columns. The reduced row echelon form of A transpose is 1, 0, -1, 0, 1, 2, 0, 0, 0, 0, 0, 0. So a basis for the column space of A is 1, 0, -1, 0, 1, 2. A basis for the column space of A has two vectors, so the dimension of the column space of A is 2, as we expected. The row space and the column space of an m by n matrix A have the same dimension. Thus, the rank of A is the same as the rank of A transpose, because the dimension of the column space of A and the row space of A are the same, but the column space of A is the row space of A transpose. So these are going to have the same, they're going to have the same rank. Okay, we know that the rank of A plus the nullity of A is going to be, is going to be the number of, that's going to be the number of columns. So the rank of A transpose plus the nullity of A transpose is going to be M, because if A is an m by n matrix, then A transpose is going to be an m by m matrix. And therefore, the rank plus the nullity is the number of columns, which in this case is m. A transpose has m columns. Okay, and because rank of A is the same as rank of A transpose, we can replace rank of A transpose in that equation. And we just get rank of A plus nullity of A transpose equals m. Okay, let's let A equal this same matrix. Find the rank of A transpose, the nullity of A, and the nullity of A transpose. Okay, the rank of A is 2. We saw that earlier. The rank of A transpose has to be 2 as well. As for the nullity of A, again, all the variables are either leading variables or free variables. The rank of A is 2, so 2 of these variables are leading variables, which means the other 2 must be free variables. So the nullity of A is 2. But the nullity of A transpose is 1, because notice what A transpose is going to look like. A transpose is going to be a 3 by 4 matrix, okay? And we'll just draw it like this pretty quickly. A transpose is 3 by 4, and the rank of A transpose is 2, which means this has 2 leading variables and only 1 free variable. So the nullity of A transpose is 1. An m by n matrix A has full row rank if the row vectors are linearly independent. An m by n matrix A has full column rank if the column vectors are linearly independent. So for example, this matrix does not have full row rank or full column rank because the rank of A equals 2. See, these rows are not linearly independent. This third row can be expressed in terms of the other 2 rows. So it's not linearly independent. And in fact, you can see that because you've got 3 rows and only rank 2. So as long as the dimension of the row space is less than the number of rows, you know it doesn't have full rank. Okay, and in the same way, you know it can't have full column rank because the number of columns is 4 and the rank is 2. If the rank is less than the number of columns, it doesn't have full row rank or full column rank. Let A be an m by n matrix. The following statements are equivalent. This is not an example, so let's scratch that. AX equals B is consistent. B is in the column space of A. The coefficient matrix A has the same rank as the augmented matrix AB. And this next example shows why, because this is not going to make a lot of sense to you right off the cuff. Okay, first, let's assume that AX equals B is consistent. Let's show it implies these other two. Okay, let A equal 1, 2, 3, 4, 5, 6, 7, 8, 9. B equals 6, 15, 24. The equation AXB equals B is consistent because 1, 2, 3, 4, 5, 6, 7, 8, 9 times x1, x2, x3 equals 6, 15, 24. As long as you have x1, x2, x3 equal 1, 1, 1. So that's a solution to this matrix equation. You can do the math and see that it works out. Why does this imply that B is in the column space of A? It implies that a solution to x1 plus 2x2 plus 3x3 equals 6, 4x1 plus 5x2 plus 6x3 equals 15, 7x1 plus 8x2 plus 9x3 equals 24 is x1, x2, x3 equals 1, 1, 1. Okay, so in other words, thus x1, and now another way you can rewrite this is, why does this imply that B is in the column space of A? It means the solution to this system of equations is x1, x2, x3 equals 1, 1, 1. Thus, x1 times 147, look at this, x1 times 147 plus x2 times 258 plus x3 times 369 equals 6, 15, 24 has 1, 1, 1 as a solution. So, B equals 6, 15, 24 is a linear combination of the columns of A, and thus B is in the column space of A. Okay, that's great. So that implies this first thing, that AX equals B is consistent, implies B is in the column space of A. Now, how does it imply this third statement? Why does this imply that the coefficient matrix A has the same rank as the augmented matrix AB? Matrix A has rank 2 because the reduced echelon form looks like this. Okay, now the dimension of the row space of A and the column space of A are both 2. When we append B to A to append this matrix B, okay, the dimension of the column space of B is still 2 because 6, 15, 24 is a linear combination of the columns of A. It does not require any new vectors be added to the basis. Okay, so that's why you don't change the rank when you append that matrix, that vector B to A. The 4 fundamental spaces of a matrix A are row space of A, column space of A, null space of A, and null space of A transpose. Let's fill in this chart. Okay, let's say the rank of A, so we have these 3 matrices, and the rank of A is given over here, and the rank of A with B appended to it is given here. Okay, first, is AX equals B consistent? Okay, notice that the rank did not change when we appended B to A. And what does that imply? Okay, notice that if the coefficient matrix has the same rank as the augmented matrix, that AXB equals B is consistent. So yeah, so the answer would be, oh yeah, that's consistent, you bet. How about in this example? Notice that the rank changes when we append B to A. So yeah, this is not consistent. That answer would be no, right? No. And then notice this one too. The rank is 2. Rank is 2. Yeah, it doesn't change. So AX equals B must be consistent. Yes. Okay, let's look at the number of parameters in the general solution of AX equals B. So notice the rank of A is a 4x4 matrix. It has 4 columns, and it has 4 leading variables. It doesn't have any free variables. So the number of parameters in the general solution of AX equals B is going to be 0. There are no free variables. By contrast, well, let's check if it's right. Yes, it is, 0. So by contrast, this matrix, whatever it's called, has 4 columns, but it only has 3 leading variables. That means one of the variables is a free variable. So the number of parameters in the general solution of AX equals B is 1. Okay, 0 and 1. Got that? How about this one? This matrix has 8 columns, but it has rank 2, which means it has 2 leading variables and 6 free variables. So the number of parameters in the general solution of AX equals B must be 6.